So we'll do our practical part of that test after lunchtime around 1 o'clock. I think I'm getting some volunteers. If anybody else that I haven't spoken to wants to volunteer, we're trying to get one proctor per test taker, so it goes a little faster for the afternoon. The written test isn't a big deal. We got that covered. So if anybody else wants to volunteer, you have to be a certified beekeeper to volunteer as proctor. Just let me know. Our next meeting, August 27 at 6:30, will be Dr. David Turby, so another expert in the field. We've had a lot of those. Thank you, Erica. Effects of urban and agro ecosystems on bees. And then if you haven't signed up, we have the Georgia Beekeepers Association Conference, September 11th and 12th up in Eastville, Georgia. I heard that this is probably the last year that they'll have it closer to us. So they may move it in the future, kind of more middle of the road Georgia. So there's the website there that will take you straight to the registration. I knew they had some special outing on September 10th. That looked full. They said 0 spaces left. So, and then our September meeting will also include our annual honey show. I would love to do a honey swap. If anybody wants to participate, you can bring some small containers of honey, you know, like the 2-ounce bears or something like that, if y'all want to share and swap honey. I like to see what other members and how their honey tastes. So if you want to bring some and participate, that's fine. If not, then we'll try again some other time. So those are the biggest events coming up. What's next in your bee yard for new people? Varroa mite. We just went through our disease and disorder class last weekend. Apologize for the rain out the weekend before. So we were talking about disease and disorders, and Varroa is a very big topic. If you guys are going through your hives and you're seeing some funny looking wings on your bees, and a lot of bees kind of hobbling around outside your hives, you can have a very high low Varroa count. So right now is the time to do your mite washes and picking your treatment. We were talking about the Honeybee Health Coalition is a good website that has your Varroa decision tools and management guides. It's like 30 pages of information on Varroa and treatments. So visit that. I believe I put the link in the newsletter. Monitor the food in your bee yard. We don't want any bees going hungry. Making sure your hives are heavy. If you pulled honey and they don't have any food, make sure you start to feed. You can use a 1-to-1 sugar syrup. I know some people don't like to feed sugar syrup, but it is an option. And always be checking for pollen. Because in the disease and disorder, Terry talked about queen problems or other diseases that can look like queen problems. So if you think you're having a problem with your queen, it could be something else, disease related, or your bees don't have enough food. So those are the biggest things to look at. And as one of our members, Kelly said, water your bees. It's very hot and they use water to keep their hives cool. Oops, that's not what I wanted. Love resources. I had somebody asking about the YouTube. We do record a lot of our things. So disease and disorder class was recorded. I don't know how long it'll take to get up there, but YouTube is, you can type in Forsyth Beekeepers GA. Again, club library, extractors, and then Lily is in charge of all of that. And again, that Forsyth Beekeepers GA right there is what it looks like on YouTube if you want to go there and catch up on some meetings that you might have missed as long as we were able to record them. And then podcasts, magazines, there's the Honeybee Health Coalition up there. And of course, Bob Benny, who was our last month's speaker, has his informative YouTube as well. And then just before we get to our speaker, I did participate in something really cool. It was creating or building the top bar build. If anybody keeps top bars or is looking or is handy in making top bar hives, Come see me because I have free do-it-yourself plans. I'm not handy, so the one I made had free drill holes, but I know I can use a drill, so it was really fun, and I'm looking really forward to starting my top bar next spring. And then when I was at Bob Benny's, since I've never kept a top bar, I got top bar beekeeping. So if anybody has kept a top bar or does other hives, let me know, and we can see if we can get together and help each other out. Anyway, now for our speaker, Dr. Keith Delapane. He recently retired from UGA, but he's an excellent speaker. I've listened to him. I was very excited to go to Young Harris, and that was my first year beekeeping, and going and listening to him. It was really cool listening about kind of trying to figure out the evolution of bees for me, and all of the different types of bees out there. So that's one of the presentations I remember him giving. He is also the author of the book First Lessons in Beekeeping that we suggest to everybody, and did a lot as the honeybee program director at UGA, and has done a lot with the setting up the certified beekeeping and stuff like that. So without further ado, Dr. Keith Delapane.
Okay. Well, thank you for that kind and generous introduction. We do have a tech swap here, and that tech swap involves the conversion from Mac to PC. So I can't promise exactly what we're going to see on the other side, but I think it'll be workable. Well, thank you. Yes, I worked at UGA. I was there for 34 and a half years and retired in July of 24. So I'm about a year or 2 years into my retirement, and everything they say about retirement is true. What day of the week is it? I'm working harder now than when I was working. And what was the third one? We had a
partner with biology.
Yeah, yes, that's it. Yeah, that's it right there. There's a third one, but I'm forgetting it, and that's a part of retirement too. So, but there's a lot of good things happening at UGA. I'm sure it's old news now that Jamie Ellis is coming on board. Jamie was my former student, and he was at 15-20 years at University of Florida. He was the guy who started the Two Bees in a Pod.
Backward, nettle.
Yeah, forward and backwards. Okay. Yeah, here we are. The Two Bees in a Pod podcast, University of Florida. That's what I'm talking about. He's coming to UGA. He is my replacement. I tell people it took two people to replace me. Because you may already know Lewis Bartlett. Lewis has been there now for 2 years, and Lewis worked for me 7 years before he assumed that faculty post. So yeah, he's at UGA. Jamie is coming to UGA, so you're going to have two bee professors there now. So that's great. When a university amplifies their investment in honeybees, that's a good thing. UGA is getting to be in the top tier universities, right up in honeybee investment, right up there with the University of California system, University of Minnesota system, that have multiple honeybee professors. Formerly Florida, but now we stole Jamie, so now he's good. So anyway, take advantage of this. UGA is going to become a real center, a world-class center in honeybee research and outreach. So that's cool stuff, right? This is a talk I put together earlier this year. I spoke at the national conference in Zamora, Spain in February, and I coupled this talk together for them. And I want to present it to Georgia audiences as well, because it covers a lot of things that I've been thinking about for the last 10 years and writing about and researching about. So let's just kind of dive into this. It's a potpourri of things about how being aware of and partnering with biology can make you a better beekeeper, make your bees more healthy. That's what we're all about. Sometimes this goes under the name Darwinian beekeeping, organic beekeeping, live or let die beekeeping. Lord, it's got all sorts of names. But that's what we're talking about, biodynamic beekeeping. See, this is just 3 titles that I sort of picked that are out there now that you can get, who touch upon some of these themes that I'll be talking about tonight. And I'm going to try to be be honest with you all and somewhat critical. Where things get off the rails scientifically, I'm going to talk about some of that stuff. Where there are things that science tells us that we ought to be paying attention to that we're not, I'm going to talk about that stuff. A lot of it you may never use, but at least you'll know about it, and it can start entering the conversation stream in beekeeping where it needs to be. And of these three, I prefer this one the most, by Tom Seeley, an venerable author whose name has been around a long time, from America. He spent his main career at Cornell, and he's just really commendable scientist. And in this book, Following the Wild Bees, he sort of throws out there some characterizations of organic, natural, Darwinian / beekeeping. They usually these practitioners, they're just averse to chemicals. They're just plain not going to use them. They don't use smoke. They think it's manipulative to the bees and too invasive. They're very curious about alternative hive designs, like the Warray hive, top bar hives, the long Langstroth hive. They're curious about that. They do little or no swarm management for reasons that we'll touch upon. They emphasize worker choice in queen rearing, which I believe is one of those off-the-rails things that needs to be brought back into correction. So I'm going to talk about that in this lecture tonight. They're tolerant of much smaller honey yields because if you're going to let them swarm, you're not going to make as much honey. And so that's just a part of the package in natural beekeeping. And they emphasize locally sourced and selected bees, and they abstain from varroa treatments. And I have opinions about all of this stuff, but I'm not going to talk about all of it. I'm going to narrow that list down. Don't worry, you won't be here all night. Let's talk first about what do bees in nature look like. And there's a lot of differences from what they look like in our apiaries. This is well, in the first place, it's a beautiful photograph, and it was made by Georgia Sumwalt. Some of you may know Georgia. She's a real active member with the GBA, and this is a photograph she made of a natural bee tree. But these, the hollow trees are the natural nest of Apis mellifera. Their entrances tend to be very, very small. The walls tend to be really thick compared to the walls in our Langstroth hives, and they tend to be fairly high up off the ground, and they tend to be, on average, about 1 kilometer apart from one another in nature. Well, what I have just said doesn't look anything like our managed bees. It's a miracle that we can take them out of those hollow trees, cram them into apiaries with 10, 15, 20 hives, and they do well. They thrive pretty well under our management. We ought to be surprised at that because it's really quite invasive of us to do that to this species. There's other points that a big difference between bees in nature and bees that are managed. And I don't have time to go through all these, but I do have time to kind of go through these bold ones. In nature, the colonies are very adapted to their location, whereas in managed, not necessarily, and in fact, probably not. They're probably from California, and then they're shipped all over the country and migrated all over the country. The colonies are widely spaced. They're very rarely widely spaced in managed ones. The cavity walls have propolis. In managed ones, they may or may not have propolis. I'm going to talk about that. Cavity walls thick. Langstroth hives are 3/4 inch lumber. Lord, if there's one thing we could change in bee management, I think it would be the insulating properties of our hives. 3/4 inch, I mean, seriously? Yeah. Colonies are untreated for disorders, whereas they are routinely treated and managed. And workers choose larvae to be the next queen, whereas breeders, human breeders, choose the larvae in managed operations. These are the main points that I'm going to focus on tonight. Just be aware that libraries could be written on all of this stuff, but we don't have time tonight. There's a couple papers I was involved in the last 10 years of my work at UGA. Both were in cooperation with a series of grants we got with the National Institutes of Health with Emory University. And it's kind of funny the hook that we used to get our funding. We said, you know, you guys are really interested in infectious disease, and how epidemics spread. Well, we have a really cool model system that we know how to manage both the pest and the host. It's called the honeybee and the varroa mite. And we can manipulate them any way we want and create these really cool models, field studies that replicate how a disease spreads in human populations. And they bought it. And they funded us for like 10 solid years. So most of everything that I'm talking about tonight comes from that very productive period in my last 10 years at UGA. And we got out a whole raft load of publications on this. And the one at the top left is open sourced. I invite you to get that. Check it out. It's open source. You can find it. Ecological and Evolutionary Approaches to Managing Disease. It was sort of a holistic synthesis of everything that we came out of with this study. And I'm going to touch upon some of them tonight. And then this bottom one right here, it talked about how the genetic structure is detectable and quite different between apiaries at surprisingly small scales in space and small scales in time. We can see detectable genetic differences in varroa mites in an apiary from the beginning of the season to the end. These guys are really mutating fast and changing genetically fast. And if you are exercising any kind of a disciplined selection program, you can expect pretty rapid change one way or the other. And there's a direction that you want, and there's a direction you don't want. And I'll talk about that tonight too. So there's a lot to talk about tonight. Right, so moving on. One of the points that we came up with that we think is really easy is, what do you do when you have a dead out? Here's an apiary. The one on the left is dead. I made the bees dead on the ground to show that they're dead. Well, what do? You come in, you take it out, take it away, and you bring in another one, right, from somewhere else? Wrong. Don't. This is one of the things we found because of those two studies I showed you earlier. You get genetic changes really fast in your varroa mites within a scale of a single season. So let's say that you're trying to breed a resistant bee, okay, and you're working at it, and you have these dead outs, and you export them, and you replace them with a package from California, and you have just blown out of the water an enormous amount of your progress toward selecting for a resistant honeybee with that one act. Import a live replacement from the same yard. This just follows the rules of good epidemiology. If you bring in fresh hosts from outside, you're giving the mites just raw, unhardened troops. I came up with that metaphor, but it seems to kind of fit. You know what I mean. Bees that have had no experience with this population of varroa, naive genetically, and they're just ripe for exploitation by those mites. And this is a surefire recipe for breeding for virulent mites that reproduce fast. Oh man, this is great, fresh meat. All right, we can reproduce really good. And that's what virulence is if you're a parasite. It's reproduction. If you can reproduce better on this population of honeybees than this population of honeybees, then you're more virulent on this one. That's what it means to be a parasite, is to reproduce at the expense of your host. So don't bring in new stock from outside. Try to stick with the stock that you've got. That's the bottom line here. Density. One of the biggest drivers of parasite and disease organism virulence is high density hosts. And it goes back to the Middle Ages, okay? You had these concentrated populations of humans in feudal Europe, right? And the plague comes through. And the countryside was relatively unscathed. It was the cities that were eaten up with plague and people died. When you have a high concentration of hosts, it encourages the parasites or the pathogens to run through them recklessly. Because it doesn't matter, there's so many of them, I can exhaust this host and jump to a new one and exhaust it and jump to another one. There's no selection pressure to be a kind and gentle parasite. You know, you have everything to gain and nothing to lose, just rip through them. So it's the same thing with our apiaries. Well, how do we know this? We did some studies, and we set up apiaries of two different conditions of density and visual complexity, because bees drift. And that's how varroa mites move around. So this is one, what we called a dense apiary. I believe we had 10 hives in each of these arrangements, and we replicated it where we had several apiaries that were, quote, dense. And they were visually monotonous. They all looked very, very similar, as opposed to a non-dense apiary where we put them in circles to minimize drifting, and we painted all these geometric symbols on front of the hive to make it easy to landmark this your home hive from another hive. And then we measured mite population growth and honey yield in these two apiary situations, right around here in North Georgia. And here's our data for 2 years. What you're seeing here is 2 years worth of data. Here's July through March, or July through October of 2015, and March through September of 2016. First of all, we found in the low density apiaries an overall reduction in mite levels. Through that same metaphor that I just told you about the plague in Europe, the hosts were farther apart. Even in that circle was far enough apart to make a difference that the mites couldn't jump from host to host so readily, and they weren't as virulent, they weren't as fertile, they weren't as reproductive. We kind of expected that. What we didn't expect was higher honey yield. The blue bars that you're seeing right there are the honey yield. It's the frames of honey, between the blue bars being the low density apiaries and the red bars being the high density apiaries. And the circles where the hives were spread far apart, even though they had the same number of hives, made more honey than the apiaries where they were all in a row. This is not a big scale. I was surprised. You know, we're talking about the scale of this room, okay? One was in a circle, one was in a line. And the ones that were in circles made significantly more honey at every one of our sampling dates. We don't really know why. We honestly really don't know why. Were they competing with each other more for nectar sources in that concentrated row compared to the circle? I don't think so. You know, not at the scale of, you know, an apiary the size of this room. Anyway, there it is. So consider putting your bees in circles. Okay, distance. This was fun. One of my PhD students, Brett Nolan, he did this, and we thought, okay, well, let's just really hit this idea of distance hard. And he had 3 different apiary situations. In an apiary of 2 hives, what's an apiary? Any place there's a beehive. So, you know, you can have an apiary of 2, okay? Well, we either had them touching 0 meters apart, or they were 10 meters apart, or they were 100 meters apart. And those diagrams are drawn to scale, just to kind of give you a sense. And then we put 300 varroa mites in just one of them. And these were the 3 apiaries, and we replicated this across Georgia several times. And we found that there was significantly more mites in those apiaries where they were close together. Among the 2 more mites between the 2 of them total, there was more mites in the 0 meter yards and the 10 meter parts. If you get them 100 meters away, there was significantly fewer mites between the 2. So this stuff is not just pie in the sky, you know, ethereal kind of stuff. It's really practical. When bees are spaced, when they're not in competition with one another, they make more honey, and there's not as much virulence among their parasites. It ain't rocket science. It's good science, it's just not rocket science. Okay? So this is, I think, is pretty practical stuff for you. One of our neighbors, Mary and Chris, around the block from us, had the fortune of a bee tree falling down in their yard. And they told me about it, and I came over and looked at it, and here we have the carnage. Bees don't do well when their tree falls down. You know, it's hardly worth trying to extract anything. There's probably not going to be much there that you can salvage. But that black sheen that you see is propolis. This is the work of years and years worth of propolis deposition inside nests. When I was a kid growing up in the 70s, propolis was a bad word. Maybe some of you are old enough to remember this yourself. The ads that ran in American Bee Journal and Gleanings said, "Low propolis hoarding queens." It's like, yeah, that's what I want. So it was a good thing if you had queens whose bees didn't collect a lot of propolis, right? We have made a complete turnaround, haven't we? We now know that that's wrong-headed. Propolis, this is kind of weird. Here's what propolis does. It turns down an immune response when honeybees are exposed to a pathogen. Turns it down. Now, why is this a good thing? Why is this a good thing? You know, the first animal that we did the entire genome for, it was us, humans. Francis Collins and his team run their project to sequence the human genome radically under budget. And so the National Science Foundation had surplus cash left over. And they said, well, hey, let's just put it up for other organisms. And the number 2 organism to be sequenced was the honeybee. And it's just kind of cool, I think, that it was funded entirely by leftover money from the Human Genome Project. But in 2002, the honeybee genome was published. I'm sorry, 2006. And one of the unexpected things that came out of that was that honeybees, compared to solitary bees, who live their entire life cycle as individuals, honeybees had much fewer immune genes that are activated than the solitary species do. An individual solitary bee who picks up an individual infection is much better prepared with immune responses to resist that pathogen than the honeybee is. It's like the honeybee has lost it. How has it lost it? Because it has made it up through social immunity. Social immunity. And this is something I've talked about and lectured about and written a book about, how honeybees evolved from solitaries into a social unit. And along the way, they picked up the ability to resist diseases and parasites as a social unit, not as individuals. So it allowed individuals to just kind of give up the fight. You don't have to invest in a personal immune system so heavily anymore. Propolis comes along and just turns that down even more because it's costly to mount an immune response. When your body is fighting an infection and your immune system is activated, it's making a heavy toll on your health. It's not for free. Immune responses are complicated things and they're expensive. And so propolis says, you know what? Becoming social was a good investment in each one of your individual immune systems because you can kind of relax and let the whole group kind of work together for our total group immunity. Each of us don't have to carry the whole load ourselves. And propolis just turns that down even a little more. Jay Evans at the USDA Bee Lab in Beltsville, whose fate is, as we all know, kind of up in the air, he published a really cool paper a few years back that showed this, that bees that are ramped up with an immune challenge, they don't survive as long, they don't make as much brood, and they don't make as much honey, and they don't survive winter as well. Just by not even expressing symptoms, just by reacting to the presence of a pathogen in their hemolymph. So propolis just turns that down and helps them survive. Propolis is good. We like propolis. Well, along comes Master Craftsman candidate, Cindy Hodges, and she runs with this idea for her project for her Master Craftsman level, which I encourage all of you to aspire to. It's the highest rank in our Master Beekeeper program, and it does require some independent research. And Cindy was interested in whether if you change the interior of a beehive, can you stimulate propolis deposition? And this is some of the interiors that she tested. She ran saw curves down the inside. She left the inside rough and unplaned. On some of the surfaces, she stapled propolis traps. You know those plastic things? Yes, I hear it. But we're in here. It'll all be gone by the time we're done. And the upshot was anything works. Anything works. And so we thought, what's the cheapest? Well, maybe the cheapest would be just to make your hives out of unplaned lumber. at least put the unplaned rough part on the interior. And I'm now starting to see people who are talking about this in the bee journals, that they're actually, it's actually one of our biggest cited papers. It came out of our lab the last 10 years. People really kind of picked up on this. It's one of those free things you can do to make life easier on your bees. Insulation. I love the fact that we're starting to see lots of innovation with hive designs and materials. This is long overdue. If you go over to Europe, they've been ahead of us for decades on this. I was visiting Poland one year, and this is an example of some of their hives that number one, they're long Langstroths. They go more horizontal than we do, and they just have lots and lots of frames side by side. But the real key feature of these Eastern European hives is the empty super on top, in which they put a big stuffed pillow, essentially. And then they put a lid over it, and it just makes a whole lot of insulation. And I'm seeing this now. You go to GBA and the different trade shows, and they got these composite materials with high RF values, and I think that's great. That's another low-hanging fruit. There's an interesting paper published in Illinois. It doesn't matter, recently. And they were interested in how the impact of removing a honey crop affected bees. And they showed that this was in summer in Illinois. They're colder than we, but not that much colder than we in the summertime. And they were able to show that the act of removing the honey crop, August, July, August, whenever they do it up there, significantly reduced the thermoregulatory capacity of the colonies. They suffered coordinating their colony temperature just by the simple removal of a honey crop by the beekeeper. They're far more sensitive than we think. Just the act of removing a honey crop, which is the whole name of the game, right? That's why we're in this business, right? To make money off of them? Right, well, I don't know. When you think about it in those terms, it kind of makes you rethink your bees, doesn't it? This was a watershed year, 1621. This is the first historical record we have of honeybees making landfall in North America. We have by this ship sent fruit trees as also pigeons. And beehives, the preservation and increase hereof, we recommend unto you. This was a manifest letter in a shipment from England to the Virginia Company in 1621. And with this comment, we have the first historic record of Apis mellifera in the New World. Big watershed moment. That has an awful lot to do with the history of the pests that you and I have had to fight with ever since. The expression of virulence, or the lack thereof, has a lot to do with the time that the honeybee and its pest have been together. That's the theme of what I'm fixing to drill in right here. Tracheal mites. Anybody seen them? Anyone experienced them? Anyone? Yeah, exactly. This is one of my points. You never hear about this beast anymore. When I came on board in Georgia in 1990, the Georgia Department of Agriculture was depopulating commercial apiaries in South Georgia if they were positive for this mite. It's microscopic. And when I showed up, it was like a proverbial hornet's nest in South Georgia, because the commercial guys were in mutiny against the Georgia Department of Ag, who were coming in and depopulating. They were reimbursing them, not at full market value, but it was a bloodletting. It was horrible when I came here initially. This pest was devastating. It had first been shown in 1917 in England. It was called the Isle of Wight disease, which is this island south on the southern coast of England. And it just decimated bees in England back then. In 1989, it was around 89, I think, it was first found here in this country. And bees just started dropping left and right. It was a very, very lethal parasite. Now with the value of hindsight, we kind of know what happened, and authorities have published some opinions about it. We already had an Acarapis mite in perpetuity. two of them. One is called Apis dorsalis. It lives on the thoracic ridge at the top of the thorax of the bee. And Apis externus likes to hang out in the neck region. This is a diagram of the thorax, and the head is cut off, but it's right here. This is the front end of the bee. And this is the two zones that these mites like to live in. And then for reasons unknown, about 1917 in Europe, there was a third one who figured out that, hey, you know this spiracle down here, which is the nostril of the bee, and here's what it looks like in real life. This spiracle covers up the tracheal tube, which is your nostril if you're a bee, and they said, hey, what's in here? And they went up there, ooh, nice and warm, and oh, this is so much nicer in here, and they started exploiting this new rich habitat that neither the Apicarapus before had ever thought of exploiting. It's a classic example of a speciation event, you know, where one species, just one population, branches off. Probably the authorities that I've read think it was dorsalis that actually made this divergence and began exploiting the spiracular environment and living inside the tracheal tubes. And it was lethal, fabulously lethal. The bees just couldn't survive it. And this is what we inherited. My professorial grandfather, Roger Morse, who was the major professor of my major professor, he made a kind of outlandish statement at the time, and he was kind of ridiculed. He actually published this. He says he and his co-author proposed that Acarapus woodi, which is the name of this tracheal one, actually evolved around 1917 from Acarapus dorsalis and parasitized this host and was very lethal. And because it was an Acarapus, and because its immediate ancestors had a long history with honeybees, it too was vulnerable to the resistance mechanisms that mellifera had already evolved against its cousins, which is grooming, picking them off each other. And so it was a relatively quick thing. It was over. It was a tempest in a teapot. About the time we started marshaling our funding to really start studying, it went away, and we couldn't find tracheal mites anymore because it was just a matter. There was so much intense selection pressure that honeybees just switched their grooming behavior from dorsalis and externus and started grooming the tracheal mite too, and voila, no hay problema. It just went away overnight. And so their evolutionary history with each other was really close. They were close kin. It was really easy to just switch over and start grooming this one instead, and problem went away. And in 2011, the Apiary Inspectors of America stopped including the tracheal mite in their annual survey of pests because they couldn't find them anymore. That's a success story. Right. Small hive beetles, 1997, they showed up. I know every one of you have seen small hive beetles. Okay. Same principle at work, but this time the bottleneck goes back to that year 1621. Okay, it goes back a little bit longer and a different continent. Okay, because the small hive beetle came from Africa, not from Europe. So there was already a bigger gap in distance and a bigger gap in time. You had an Apis mellifera from Africa compared to an Apis mellifera in North America who came from Europe. So you see, things are getting a lot more distant in space and time. That story was a little different. And this is what my former student, my successor, and your future honeybee specialist, well, he's here now, June 1st was his start date, your current honeybee specialist in Georgia, Jamie Ellis, this is what he did his doctoral dissertation on. We set up apiaries in both South Africa. We had USDA funding to do this research in South Africa as well as Georgia, so we replicated this study in both. We set up colonies of Apis mellifera scutellata, which is the classical Eastern African killer bee, we call it over here in this continent, and just ordinary Georgia Italians. And we inoculated one set of apiaries with small hive beetles and the other one without small hive beetles. And just recorded stuff. And what you're seeing here is the difference of colonies in both locations. Right here we have, South Africa results, and here's the Georgia results. No differences in brood area and bee population. These numbers are not significantly different. In fact, they had more bees in South Africa in the colonies that we inoculated with beetles. Go figure. Down in Georgia, on the other hand, a very different story. Significantly less brood, significantly fewer honeybees. Small hive beetle is a much bigger problem here than it is in its natural region of South Africa. And it still kind of lingers to this day. It's not the benign little puppy dog that tracheal mites have turned into, is it? If you have a heavy infestation of small hive beetles toward the end of the season and the hive is already kind of compromised, it's toast. You know, the beetles will just overrun it. So we're not quite out of the woods yet when it comes to small hive beetles. The resistance mechanisms are too far apart in time and space for our bees to rapidly react to this new threat. Distance in time and space matters. Now let's look at the biggest one of all, Varroa. This is where things get really remote in time. This is a map showing the modern distribution of Apis cerana, the blue zone. And this is the natural host of Varroa destructor mite. This is the natural host, this is the natural range of Apis mellifera. The Varroa on Apis cerana never made contact on mellifera until the mid-20th century, thanks to human trafficking and movement. In Southeast Asia, on the other hand, every bee has its native mite. It's such a tidy little relationship. Each bee has its own mite. It's like the rhinoceroses in Africa, that each rhinoceros has its own, bird that perches on its back and is so. And everyone gets along fine because it's a long evolutionary relationship. The bees can tolerate a few mites because they don't overrun the colony. They've learned how to contain them. And the mites sort of persist because they always sneak a few generations in each year, but they don't overrun their host. That's what happens with an evolved relationship. But when it's unevolved, it's unnatural, we call it, like it is with Varroa and Apis mellifera today, all chaos breaks loose. And we're still living under the reverberations of the 1987 introduction of Varroa into this continent. Mellifera has no evolved mechanisms against it. Zippo, nothing, nothing. There has been success in breeding though, hasn't there? We all know about these things. But every one of them is a trait originally evolved for another pest. Hygienic behavior. The ability to detect a cell of brood that has a Varroa mite in it, uncap it and pull it out and throw it out the door, was originally evolved for foul brood, American foul brood, not European, American foul brood and chalk brood. But now it's been co-opted into expressing if there's a Varroa mite under that capping or not. But it was not originally evolved for that. It was totally alien to it. Grooming behavior. The Purdue mite biters, they call them. Purdue's my other alma mater, by the way, so I got to take some pride in that. But the ankle biters that Purdue has developed, they can pick mites off of one another. The Browla louse was its original stimulant for that behavior. So we can force a round peg into a square hole, so to speak, and force a hammer to be a surgical scalpel if we must. If that's the only tool we have, we'll figure out how to use a hammer to do so. You see what I'm saying? They're using a different tool in a way for which it was never evolved. And it's the jury's still out if it's working or not. Okay? There's another way that breeding sometimes works with Varroa. And it's the principle of a generalized reaction to a pathogen or parasite. Think of what you and I do when we get, what's this thing that's going around in the lettuce? It's making headlines. What's it? What is it? Okay. Cyclospora. Yeah, well, just imagine that with me for a minute. What does your body do if you've got it? I can predict. Your gut is going to empty itself. thoroughly. Okay, that's the first thing that's going to happen. If you have other, like a respiratory, pathogen of some kind, you're going to sneeze, you're going to cough, you're going to, your gut's going to expel, you're going to have a fever. What the heck is a fever? I mean, a fever is an elevation of the body temperature to hopefully reach a lethal high that will kill the pathogen but not kill you. If you have an injury, if you break or you have a breach of the skin or break a bone, your tissues swell. Well, why are they swelling? If you get stung, it swells. That inflammation, what is that? Well, we know chronic inflammation is bad, but what's acute inflammation? Well, it stiffens up your tissues so that the offending invader cannot spread as easily. It's a method of containment. These are generalized responses. That only what I just said could describe 1,001 pathogens, couldn't it? It's what you do when you're just sick. And your body's like, mayday, mayday, repel, repel. You do all that stuff, okay? Well, that's not a specific response. That's not a targeted, specialized response. That's a generalized response. Honeybees do that for Varroa as well. It just looks different. If you are under stress, mayday, mayday, something's attacking us, what are you going to do? Let's swarm a lot. Let's just swarm. Hey, we got more brood. Okay, swarm again. Hey, okay, we're recovering. No, swarm again. And so you get these repeated swarming events, and your populations never get big. They just always stay in build-up mode, and they barely collect enough honey to survive winter, and maybe they had enough to survive, and maybe that really is a form of genetic resistance to Varroa, but it's not a targeted resistance to Varroa. You see, what do you do if you're Apis cerana? You build this nifty little chimney on your drone brood. It looks like a little elf cap, okay, with a little open chimney on the top. And Cerana has a nice deal worked out with Varroa destructor. Like, guys, come on. Take our brood, take our males. They're expendable. You can have all of them you want, seriously. But they still make these little elf tops on top of the drone brood. We don't know why. But somehow that limits the Varroa just to male brood and not even all of it. So they have evolved these are specialized responses to Varroa. And Mellifera has not had time to do that. Okay? So just be aware that when we blithely talk about, I'm going to breed Varroa resistance in Apis mellifera, just understand what you're up against. You're up against about 7 million years of inaction. And the inaction is profound. It's not just in time, it's in space. Because of a paper published in 2013 has put forward a very powerful argument that the genus Apis actually evolved in Europe, not Southeast Asia, and that it had 2 immigration waves. One that, well, I'm going to try to do this mirror image for y'all. Here's Europe, Germany, France, where the oldest fossils to this day exist of the genus Apis, all honeybees. Germany, France. One lineage goes down into Southeast Asia, and there it explodes. It's a very successful habitat. It radiates and makes about 9 species of Apis. Another lineage goes down here into Africa, and it explodes into just 1 species, Mellifera. And by this model, which is one of many, I have to be honest with you, this is not settled yet, but probably the strongest model when it comes to fossil evidence is for an European origin of the genus. By this model, Mellifera never encountered an Asiatic mite, ever, in its evolutionary history. It's why it's so intractable for us today to breed a resistant honeybee, Mellifera, to Varroa. Right, in the interest of time, I'm going to kind of move on. I've made these points. There's other reasons why Um, have you ever wondered, I know I have, why do you have to replace your genetically improved queens all the time? Yeah, okay, I'm going to get hygienic queens. I'm going to get Minnesota Hygienics or VSH Hygienics. I'm going to start introducing them to my apiary. Well, why do you have to keep doing that? You do it, okay, well, they're I still have to treat with chemicals, but anyway, I'm still doing it, and the next year you got to do it again. Why does that trait just sort of vanish? Why doesn't it just take hold? And it should take hold, shouldn't it? It's varroa mite resistance, for Pete's sake. I mean, why does it dissolve away? Well, there's reasons for this. And this is good biology versus bad biology. Evolution doesn't really like selecting for extremes. It likes to select for normal. It likes to select for the population average. What happens if you're really a standout? Yeah. What's going to happen? What could go wrong, possibly? And this is true of population scale evolution. Very often, evolution pushes a population toward an average. They don't like to have extreme varroa resistance. They don't like to have extreme honey production. They don't like to have extreme American foul brood resistance. Name whatever trait you're interested in. Evolution never pushes it to the extreme of any one of them because it's costly to invest all of your eggs in one basket like that. So very oftentimes evolution tries to shift to an average for that population. Our challenge is to try to shift our varroa resistance toward a higher average than where it currently is. There's a paper that came out, published by Lewis, my first successor. I had a better image of this. This is a Mac and PC thing. I'm sorry. It was really cool. I had the masthead of the journal and everything. It was a nice paper that they put out in the Proceedings of the Royal Society. But it's called, and those of you who have a background in economics will enjoy the pun here, Avoiding the Tragedies of Parasite Tolerance in Darwinian Beekeeping. The Tragedy of the Commons is a famous economics paper that uses that term. And what these people were saying is, there's a problem with Darwinian beekeeping here. And what is Darwinian beekeeping? Let's just jump to it. Oh, darn it. I had a really cool image here that didn't transmit. Okay. There's resistance, and then there's tolerance. Same thing, right? No. Not the same thing. Let's say I'm going to be a good Darwinian beekeeper, and I tell you what I'm going to do. And this actually has a name. It's called the Bond method. Bond. James Bond. Live or let die. Dun, dun, dun. Live or let die. Because that's what they do. That's what they do. And this all started with a scientist named Ingmar Fries, who's a Swede, and that's the map here of Gotland off the coast of Sweden. And Ingmar Fries said, I'm going to practice a James Bond approach. And I'm going to set up an apiary on this isolated island of Gotland that has no other bees on it. And I'm going to inoculate them with varroa, and I'm going to walk away. And we're going to come back next year and see what's left. And he did that, and he came back, and there was one or two left. But it was mass carnage, you can imagine. I mean, 99% of them died except for these. And they took those, requeened them, propagated them, started all up again, and next year, 5 hives survived. And the next year, you know how it went. So they now have essentially, or they did, they've abandoned the project now. But they came up with a bee that just pretty much lived forever without varroa mites. And this became a real inspiration to the Darwinian crowd. Man, we're going to do this. It's so easy. God, all you have to do is just put the bees out and let them die, and those who live breed from. Well, anyway, this goes back to that tragedy of the tolerance, the tragedy of tolerance. Because unless you are really watching what's going on, you don't know what's going on. You might be getting a resistant bee, that is actively resisting the varroa mite. And by definition, a bee that resists varroa is subtracting the mite's reproduction. It's affecting its reproduction. It is decreasing its reproduction, or it is not expressing resistance. That's important. That really makes a big, crucial difference to everything. A tolerant bee, on the other hand, has just figured out how to survive. The mites can chew on it and it lives. Mites can spread viruses in it and it lives. It's just really good at living under crappy conditions and just ekes along. Well, what's so wrong with that? Yeah, they're staying alive, right? Well, what are the mites doing? When this is the situation for the mites, here's what happens to the mites. It's like, thank you very much. You couldn't have made my life better, because I can reproduce at maximum rates at no cost. My host doesn't exact any cost on me. Bring them on. And I'll just reproduce. I'll make 10 offspring in each brood cell if you want me to. Bring them on. That's what happens when you have host tolerance. You're breeding for hypervirulence in those mites that are left. This is bad. And this is the genesis of what has become known in beekeeping